Good afternoon, everyone. We share the screen until people joining. Okay. Let me open also the chat here. How is everyone doing? How are you guys? Great. Can you see my slides? Okay, perfect. Before I start today's lecture, I want to just make the announcement about the mock-up test that I posted on the course link. I hope you guys had a chance to see this announcement on the course link. So this basically is a sample test. Yeah, sorry, I keep, yeah, let me just enable this first. So basically, this small little test is an online test using the quiz tool on the course link. And just give you an idea about like how will be the midterm exam look like. It's going to be similar to this. Might be some multiple choice questions and written problem. So what you have to do is, like, for example, look at the problem, solve it on a piece of paper, and then upload it as a PDF. So please make sure that everybody's hearing this. When you actually upload the file on the course link quiz tool, it's like we like to have it as a PDF so we can have access to grading and other things. We're not able to access the quiz. Okay, I will check that. It should be. Do you see it or not? Do you see the link to the quiz or no? Anyone? There's no quiz feature for us. Okay, the midterm next week, right? No, not next week, right? The midterm should be, is it March 1st? Let me just open the course outline here. Just double check the time for the midterm. Midterm is March 1st. Okay, so we still have time to, okay. Okay, let me see this after I finish the lecture today. I will make sure that you guys can have access to this. But it's like you have basically have like, from now and until the end of February to do this trial. Didn't finish the last example last time. I don't have time, sorry, Layan, to go over this. If you guys can stay around and we can go over this example, but unfortunately, like, I'm very behind when it comes to the course material. So I assume that you can either ask the TA while doing the problem analysis session, or come over like after the lecture, and we can sit down and solve it together. But I did post the solution when I uploaded the material, the updated material, so you will see the solution there. Okay, so let's get back to what we need to finish today. So today is a new chapter. I think I consider this chapter is a very important chapter in the fluid mechanics course. And let me, sorry for keep repeating this, but let me remind you about the main objective of our course. That is basically we're trying to understand some fundamental of fluid mechanics. Okay, so I mentioned in the beginning of the course that fluid mechanics is usually covered through many courses. Okay, fluid mechanics, advanced fluid mechanics, even fluid mechanics basic, it has like 2 courses. And also some hydrodynamics, some compressible flow, turbulent flow, and other courses, right? So what we are trying to do for this one course that we are taking in our curriculum is going over the most important pieces of information that allow you to understand how to deal with fluid when you have fluid involved in your system of analysis. Okay, so so please, when we are going through these materials, some of the material kind of, I know I don't have time to really cover it because of the limitation in the course, but I will be always focusing on the most important, concept that everyone should know about fluid mechanics. So the concept of fluid flow is one of the most important analysis that we're going to deal with as an engineer, because most of the time we have fluids, flowing from a point A to point B, from one component to another component in a system. Where, majority of this application is dealing with fluid motion, and this fluid motion, I mentioned to you in the beginning, in the first lecture, that is, can be involved like from a large bar scale power plant to a simple food processing facility, right? So it is in a wide range of application, or even the blood vessels in the human body. Like all these kind of application is dealing with fluid flow. So Frank White textbook that we are actually using as a guideline for this material is covering this analysis over 3 chapters. Okay, the first chapter is considering, chapter 3 is considering the control volume type of approach. Chapter 4 is talking about the differential or a small scale analysis, like what you see in, for example, the fluid, every velocity around the car. For example, if you are building or looking at the velocity distribution around the cars, or a small little detail information that we are interested in. So this is going to be covered in chapter 4, again briefly. And then in chapter 5, we are going to look at what type of application where it's very hard for us to do some analysis using analytical model or modeling, or we are using somewhat we call it the one-dimensional analysis or the experimental method in order to verify the analytical solution. Or if we cannot solve the problems, we have to really change it in a way that we can do the analysis experimentally. Okay, so let's keep closing. So basically, our objective for chapter 3 is to develop understanding on how to analyze this fluid in these different systems, and also we look at what we call it the conservation law for fluid flow. Okay, we're gonna repeat some of the stuff that we talk about it maybe in the physics when we're talking about the conservation of mass and the conservation of momentum and the conservation of energy, but we're gonna apply it to a fluid motion type of analysis. Okay, and then we'll look at what we call it special case of this analysis using a simple frictionless model, like assuming the fluid is ideal, there's no friction, right? How are we going to deal with momentum and energy analysis for this? And we're going to develop something called the Bernoulli equation for that. Okay, so I'm using the material from Frank White in this case. And let me start with just giving you an idea about like what we talked in the beginning of this course, that, some of the application, for example, like what we see here as a power plant. It could be a nuclear, it could be any system, right? But imagine this system or a big, facility that we are talking about. It's consists of like multiple components. Like, for example, a boiler here, right? And then, the fluid going into the turbine. The turbine is actually, generating this mechanical motion, and this mechanical motion is converted to the electrical motion in the generator here, and maybe the fluid will come back again here, and so on and so forth, right? So you can imagine that most of the engineering system consists of multiple equipment and multiple components, and in between this component you might see fluid is flowing in this system. Okay, so there's 2 ways of looking at this system. Either you look at the system as an overall, like, the whole plant, right? You can do the analysis to see how much, for example, kilowatt hour here, for example, generated out of this plant, right? Versus how much, like, fuel that you are adding here. Okay, or you can look at every component. You can look at this pump here to see what is coming into the pump and what is going out of the pump, right? Or what is coming, in the boiler here, right? So that's why we're going to define something called the system. And you will understand this in much more detail when you are taking the thermodynamic course. But let me share with you a very simple, kind of example to what the system means. So the system definition is your interest, your the area or the component or the region where you are interested in. So we call these is our system, right? And we surround the system by kind of an imaginary an outline like this, and we call this outline, we call it the boundary. Okay, so what is in basically the boundary is what is separating your interest from the surrounding, and the surrounding could be the environment, or it could be the component just beside it, beside the one that you are basically selecting, or the small little system that you are selecting. Okay, this is a general concept that you're going to learn in thermodynamic. But in general, system is your interest, domain that you are looking at. The boundary is what is bounding the system, and then whatever outside is, we call it the surrounding. Okay, so this is basically the definition I was talking here. So boundary, it can be an imaginary boundary, because you remember when I talk about like the pump, for example, here I put like a dotted line around the pump, so I'm imagine this is now my system, right? Or it could be an actual boundary. For example, if I'm looking at the room that I'm sitting in here, and I'm gonna study the whole room, so I'm gonna look at the walls and the ceiling, the floor. This is my boundary, right? So it could be an actual physical boundary. Okay, two types of analysis that you're gonna study in the thermodynamics, but just giving you an introduction here. Something called a control mass and something called the control volume. So the control mass is when you look at the mass, and again, we're dealing with fluid here, right? So every time we're talking about mass, and it's basically the mass of these fluids. Let's say, for example, the air coming from the vents in this room, right? If I talk about the air that is coming, the mass of this air coming, and I follow this mass, like I just go with the mass and see where this mass is going, what is the velocity of this mass, and so on. We call it a control system approach, okay, or control mass approach. Control system or control mass are the same name for this type of analysis, okay? Versus something called the control volume. So control volume mean I only look at the boundary as a fixed volume, right? And I see what is coming in or what is going out of these boundaries. Okay, so selecting a control volume and then see what is crossing this. What is crossing this in terms of mass, or what is crossing this in terms of energy? Okay, and a simple example to this, like when I have a piston here, and this is a cylinder, and this cylinder piston can be moving up or down, right? So now if I have a certain mass inside this, let's say, for example, I have some, maybe gases inside this control system. If mass is not crossing, if there is no mass coming in or out, that means we call this is a constant mass system, okay? But also I can maybe heat this, right? I can maybe add amount of heat here, right? I can push this piston down or this piston up, which means that I have work here, like energy that is moving this piston up or down. So energy can transfer in and out, but mass cannot for this specific system, and that's why we call it the control system approach. For example, if I heat this, the piston will go up like this, right? And the gas volume will change, right? But the mass is still the same because it is trapped inside the piston cylinder device that I'm showing here, okay? Versus the control volume is, as I mentioned, the control volume is a boundary that you are selecting. And let's say, for example, it is a real boundary here. Let's say that this is a nozzle. A nozzle mean here, it's some kind of converging area, bigger area going to a small area, right? And it's made this way in order to change the velocity. So the velocity 1 here, the velocity 2 here. We're going to talk about this in this chapter. But it's like I selected this control volume. okay? And I see what is coming in as mass and what is going out of this mass, okay? And of course, energy also can be transferred in or out, okay? And it could be not a fixed boundary like this. It could be a boundary similar to the one that we studied before, but now you have an inlet here. So you have a mass that is coming into this piston cylinder device, right? So you have a mass coming in and the piston goes up or down, depending on if it's the mass coming in or out. So you can have what we call it like a moving boundary. So the boundary here is this, right? But because the piston goes up and down, so this volume changing, right? So in this case, I'm still considering the volume here, okay? But I'm only seeing what is coming in or what is going out of this, right? Control volume is not a constant volume. So you can see here from, figure B here, that the volume itself is changing, okay? But the shape of the volume or like, the boundary is either squeezed or like, expanded, right? But you still kind of, taking this specific volume. We call it, for example, here, the internal volume of this cylinder and so on, okay? This is all background to this chapter, just before we start, okay? Another very important definition before we start this chapter is something called velocity profile, okay? What is a velocity profile means? Is basically velocity distribution, okay? So, if I need to find out velocity distribution, you guys know how to plot charts, like, the velocity at different point is equal different value. I can just, make an X and Y plot and find out the velocity distribution, okay? But, commonly in fluid mechanics, we call it the velocity profile. So if I have a pipe like this, what will be the axis appropriate to plot the velocity distribution or the velocity profile is maybe axis Z, right? Maybe the radial direction. So, and then maybe theta, right? So the cylindrical coordinates will be the best to describe the flow inside the pipe. So Z could be the axis and R is the radial direction, right? And basically theta is, the circumferential of this. So the tangential kind of direction for, the angular direction at a certain location. If in order to plot the velocity distribution, maybe I can just, let's say, for example, I make a line like this. Can you tell me if this is the center and this is the wall, right? From our chapter 1, remember, we were talking about viscosity and the velocity, of the layer of the fluids. What is the velocity at the wall here? Can you tell me what is the velocity at the wall here? This is a pipe, and I'm calling this wall here. Every time we talk about wall, that means we are assuming the velocity at the wall is 0, right? So if I plot the velocity distribution, basically at the wall is 0, right? And of course, if I go all the way around the wall, it is 0, right? Where is the maximum velocity here, do you think? Where is the maximum velocity? If I have a fluid that is moving in this direction, okay, where is the maximum velocity? At the center, right? At the middle, right? So basically, if I plot the velocity here, I will see something like this. And I call this is basically the velocity distribution, okay? And the center here is where the shear stress, if you remember the viscosity, is, the center is the farthest point from the wall. That's why the velocity in the center will be the maximum. And of course, we're going to learn in this chapter what is driving the fluid in this case, okay? How the fluid will move inside this pipe. What is the driving force, okay? Of this fluid in pipe that is basically a fixed pipe like that, okay? So we'll determine what is. But the velocity distribution here is basically is something like that, okay? So at a certain R, I can find out this velocity here, Okay, so if I look at this is the velocity at a certain r, right? At any point, far from the center, I can find out the velocity distribution. Okay, how about if we have a parallel plate like this? Okay, and I'm gonna plot again the velocity distribution. But if this is plate, basically the appropriate coordinate for this will be Cartesian coordinates. So this will be our y, this will be our x, and if you want, this will be your z. Okay, so I have one plate is moving with a velocity u capital, and one plate that is fixed. And let's say this is our wall here, okay, or a fixed wall. People don't confuse. Okay, so the velocity at the wall is 0. The velocity at the plate that is moving with velocity u capital is u, right? So if I need to plot the velocity distribution, something like this. And remember, the velocity distribution could be any equation or any function, right? It doesn't have to be linear. Nobody said it's linear here, right? It's just like a velocity that is equal u capital, right? This is, of course, the velocity distribution here, x and y. What is this distance here is a scale of the velocity, right? This is how many meters per second. This is a less meter per second. This is less meter per second. This is less and less until it's 0 here, right? So you can just look at this as the scale of the arrows that I'm actually plotting here is the scale of the velocity. The more the velocity, the bigger the arrow, right? So we call this is basically what we call it velocity profile. Okay, and this is very important to understand fluid flow, right? Okay. So there is another also important definition we have to keep in mind. Wouldn't be velocity profile linear? No, I think we spend a lot of time discussing this. The velocity profile, the linear, okay, the Newtonian fluids is the relation between shear stress and shear strain. This relation is linear, which means that shear stress or tau equal to, it is proportional by du by dy. We remove the proportional sign and we put equal constant. We call it the viscosity. Okay, so shear stress versus shear strain are linear. That means it is non-linear. It's a Newtonian fluid. But the velocity profile, the velocity distribution, it doesn't have to be linear in a Newtonian fluid. Okay, uniform flow, another important definition that we're gonna hear in these chapters. Okay, and uniform flow is referring to an ideal flow. Okay, and the ideal flow here in this case is is indicating that the viscosity is 0. Okay, so ideal flow, it means it's an imaginary flow. Okay, just like So do we have a viscosity of 0 to any of the fluids? Any of the fluid in real life? No, right? But it's an approximation because sometimes it's very helpful to put the viscosity is 0 and do the analysis for any problem to simplify the problem, and then just get an idea about what's going on. And then once we know this, we can actually make the problem a little bit more complex by including a viscosity. But you will hear something called uniform flow. Okay, and uniform flow in this case, if we have an ideal flow, right, or an assumption, right, that we use in order to analyze a problem. In this case, the ideal fluid assumption here is basically looking at the velocity distribution in the pipe like this, and you will see the velocity is constant. Of course, this is only available if mu is equal 0. No shear stresses between the layers, which means that the velocity is the same. Because what changed the velocity between another point far from the wall is the viscous forces between the layers. Okay. Again, all these are concept and definitions. Okay. Sometime for plate, for example, right? There is something called far field flow, and you will find a lot of environmental engineer actually dealing with these kind of things when they are looking at the weather, for example. So they are looking at the velocity distribution around cities. So these kind of, this could be the ground, and something called far field flow mean like, something like this. So if I put the velocity distribution, let's say this is our X and this is our Y. Okay, the velocity is very small, very close to the ground is 0, and the velocity is increasing to a point, and then far from the, far from the building and stuff like that, the velocity is approximately, constant. Okay. So you might see, of course, building here and stuff like that, right? You might see a velocity distribution here, and then as you go in an open, we call it the far field, you can see the velocity is becoming approximately constant. The velocity is constant along the way here. So we can call this is a uniform flow. Okay. Those are the location where we're going to hear about this uniform flow, either in an assumption that we consider to see what's happening, or we can look at an ideal flow and then do the analysis. Okay, this is a kind of, basic definition that we are going through before we start the chapter. Another important definition is talking about something called volume flow rate. Okay, volume flow rate, or we call it the discharge. Okay, in our fluid mechanics subject, we call it discharge. So this Q here is a volume of liquid that passes through an area per unit time. Okay, imagine I have something like this. This is a tube, and this is an area inside this tube. Of course, the cross-sectional area here will be a circle. And imagine I have a constant velocity. Okay, so I have a constant. I'm going to call it again. Let me just call it a better name. Average velocity. Okay, so the velocity at every point here is the same. That's not a uniform flow. It's just like, let's imagine now it is a velocity that is uniform, right? Or I assume that I have a certain value. I just take this value from this profile and change it to some other number that is average value of this number is a certain number, right? Now, for this area to move in this direction, imagine now this area moved a distance L. Okay, so what will be the volume moved in this case? What is the volume moved? Imagine now this area is moved the distance L. Okay, so the volume will be this area, right, times L, right? So basically the length times A, so this L here times A, this will give you the volume. Okay, so now what is L here? If I have a velocity V, the velocity is distance divided by time, right? Now if I consider this now, what will be the velocity here? So the velocity is distance, this is L, divided by time, delta T, for example. So the L here will be equal what? L will be the velocity times delta T. So I can remove this distance L and put it as the velocity times delta T. Okay, now I change the volume into something like this. So the volume now, I just call it like this. Volume is the velocity times delta T times the area. Okay, if I divided both sides by delta T, delta T. Now I can call this is what we call it. This is volume. And this is time. I can call this quantity as volume flow rates. Okay, so anytime we are calling a quantity with respect to the time, we are basically referring to the rate of this quantity. Okay, so the change of this volume with time is basically our volume flow rate. Okay, I can call this quantity here as Q. Right, so you will see a lot in the fluid mechanics subject that there's something called Q as the volume flow rate. Okay, or we call it the discharge. Okay, so this discharge. Okay. So this is another important definition. Keep in mind when we are getting into our subject for today. Now, what is the difference between volume flow rate and mass flow rate? Okay, we know that density is m over v. Therefore, mass is equal rho v. Here v is a volume, right? So mass here is rho v, right? So I can, for example, find out the rate of the mass or the mass flow rate by divided by delta T, or this is the mass flow rate. And sometimes, we call it m dot. So m dot here is the mass flow rate. So this volume over T is basically our Q, right? So V over T is the volume flow rate, right? So rho times Q. So this is mass flow rates and this is volume flow rates. Okay, so the difference between the mass flow rate and the volume flow rate will be the density. Yeah, so I'm just explaining here what I mean here. So if you are looking at the mass as a derivative, yes, of course, you can do this as, delta mass, or right? But I'm explaining the concept here of the ratio, right? But of course, mass flow rate is a small mass. If you consider the small mass is m or the small mass is delta m, that's going to be the thing, right? So those are the relations, right? Okay, so just all this kind of basic definitions before we actually getting into this chapter here, right? But the mass flow rate here is another definition that we are interested in. Let's get into our topic for today, right? So our topic for today is looking at volume flow rate for an actual velocity profile. So imagine you have a fixed plate and you have a fluid that is pushed in between these two plates. Okay, of course you're gonna question how the fluid will move. The fluid will be basically moving in this case here, under the pressure effect. So you are pushing fluid. So now the velocity at the wall, the velocity is zero. The velocity is zero. And in the center here, it will be the velocity that is maximum. Okay. And the velocity profile, this is our velocity profile. Okay. At any distance y, the velocity is v. Okay. So at any distance y, the velocity is v, right? So the velocity profile is, the velocity is basically function of y, okay? Or the velocity profile here is v of y. Velocity as a function of y. Now, if I need to find out the flow rate is, in this case, if you remember in your mass, when you have a variable function, right? In order to find out the total value for this function is basically you are integrating over, right? So I know, for example, here, let's say dq is the velocity times you see here, if I look at this, This will basically dA, right? So if I imagine I have an element, when I look from this side here, so this is basically what? This is something like this, right? This distance is dy, or this area here is dA, right? And the velocity is going like this. So this is a velocity that is function of y. So I can say that the velocity that is function of the y times dA will give me the differential or the small little dq. If I need to find out the total q, I just need to integrate over this. So dq here will be our q, and basically the integration of the velocity dA will be basically giving me the total. If I need to look at the mass flow rate, the difference between this equation is just like, the density is multiplied in order to find the mass flow rate. So how about if the density is constant, and when this is when the fluid density is constant? Just give me a sample for this when we have a density that is constant. Anyone? When can we assume the density is constant? Just factor out. Oh my God, no. No. Density, guys, chapter 1. Incompressible fluids. Excellent, Aiden, right? So density is constant for incompressible fluid, right? When we have, right? Like, for example, give me an example of a fluid. Liquid, yes, Colin, right? So we have liquid here. For liquid, density is constant, right? Like, for example, liquid here. So I can take the density out of the integration, and we can just say it is rho times the integration of VdA. Okay, this is all definition when we are getting the velocity distribution. Mean velocity or average velocity. Okay, it is basically, I have a velocity profile like this. I need to find out the total Q. I can find the total Q by this integration, right? So I have this Q here. So I do the same thing here. I just get the Q like this, right? The velocity is, water, milk, any liquids. I think we can consider the velocity is, the density is constant, right? Now, average velocity here mean, we just need to get the average value, right? You guys in the math, when you have a function like this, you can take the average of these functions, right? So it's a very simple concept. The average value is when you have a variable function or a variable variable, right? So you have variable quantity, right? And you need to get the average of this quantity. So you just take the whole, you integrate over the whole area, and then you divide by the total area, right? So in this case, this will be the integration of the velocity times dA, or the velocity integration over the area. If you divide it by this is the total area, total cross sectional area, right? It will give you what we call it the average velocity. And I put the bar here as this is basically an average velocity, or is equal to, basically this is your Q divided by the area, okay? Or I can take from this equation that Q is equal to area total times V average. So this is total and this is average. So if I know the total area and if I know the average velocity, I can find that Q, right? And this is very, very common in our fluid mechanics analysis. So we have the velocity in the pipe 3 meters per second. This is mean average velocity in the pipe, like at the cross section, that's 3 meters per second. I can get the area of the pipe and I find out the average velocity. Yeah, some people raising hands, I don't know. You can put the question on the chat. I can read it. Okay. So basically, in this case, if we have a total area and I have an average velocity, I can look into the total flow rate as average area. Average velocity times the total area or cross-sectional area. Okay, right. So starting in this chapter here, we call it, the conservation of mass. Okay, the conservation of mass is an important law to govern the fluid flow in a system. And in order to understand this, there is something called Reynolds transport theory, right? I'm going to apply it only for the mass conservation. I can explain it to you in the mass conservation as in this slide here. For the momentum and energy, you guys can either read and understand more, but we're going to only look at the final result out of this analysis. Okay, but it's a similar thing. Imagine I have a tank here. So I have a pipe. And there's a pipe out here, and I have a tank here. And let's say we have mass coming in, mass in, and there is mass out. Okay. I can also say mass flow rate in and mass flow rate out. Okay. Let me ask you something here. What part of the math? It's not a math. It's an understanding of the fluid flow in a system, right? So we know because of the viscosity of the fluids, when you have a fluid between plates or a fluid in a pipe, we expect a maximum velocity at a certain point that is far from the wall, right? So in the pipe, the farthest point from the wall is the center. So that's why the velocity is maximum at the center. Okay, but for a flow between two plates and one plate is moving, with a certain velocity. Now, what is driving the flow is the plate. That means the maximum velocity is the plate velocity, right? So it has nothing to do. But average, yes, average velocity is looking at the average quantity of the flow rate and divided by the area will give you an average flow rate. So this is the mass. If you are referring to the mass, it's going to be the average velocity, not the maximum velocity. So now let me ask you a question on this picture here. So imagine I have a tank here and I have a pipe that is carrying mass coming in, and I have a pipe that is carrying mass going out. Okay, let me just explain, guys. Just wait a few seconds and I will explain. Okay, so I have a tank, I have mass coming in and mass going out. Now, imagine I have mass coming in that is much greater than what is going out. What happened? Let's say, for example, let's say it's water here, okay? And this is a tank, right? So this is basically, this is my tank here. Let's say, okay? So I have mass, a lot of mass coming in, but only a small amount of mass going out. What do you think about the level of the water inside this tank? Increase or decrease? Increase. Anybody else? Anyone have a doubt that is going to decrease? No, right? How about if I have mass out that is much more than what is coming in? So in this case, right? It's very simple, right? So the conservation of mass is basically dealing with this. Okay, the conservation of mass is dealing with this. We assume, or we mentioned in the beginning of these slides that we're going to talk about something called control volume approach. So control volume approach is talking about a system, and let's say this is my system now. Okay, this is a control volume. Okay. And this is a control surface or the boundary that we are talking about, okay? So this is a control volume, and this is basically the boundary. And this is basically, right? So MCV, right, the people were asking, is the mass of the control volume. So this is basically the mass of the control volume. But at any time t, So at a certain time t, this mass is that much, right? Maybe after 1 second, 2 seconds, this mass might change, right? So that's why we put it as the mass of the control volume at time t. Okay. Now, in order to understand how the Reynolds transport theory is working, he's saying that basically your system at a certain time t is including a small little mass, just like if you imagine you are freezing the time, okay, at a certain time t, this mass, a small little portion of mass, is gonna go in, right? So you basically say that the mass of the system that we are considering here is this whole mass plus a small little piece that is coming in, okay? So now just take a picture of the time, and this mass is about to come in, and I consider my system is including this piece of mass or the small little mass, right? So I'm called the mass of the system is mCV plus delta mn. Delta mn here mean the small little mass that is very small differential element, almost like a drop that is just coming into the system, okay? Now I'm gonna, go after a certain time delta t. So this is at the time t. At a certain time delta t, right? The mass of the control volume here is change, right? You see here the mass of the control volume at time t plus delta t. Okay, so after a certain period of time t passed, right? Of course, here we're talking about very differential elements. So we're talking about a very, very fast. I'm talking about almost at the same instant, but I'm thinking as if I froze the system at time t, and I froze the system at time t plus delta t. In the first part here, the mass that was coming in, now at the time t plus delta t, there's mass going out. Okay, so this mass here, that is going out. So my system here become what? Or the mass that I'm considering now is mass of the control volume at t plus delta m out. Okay, in order to find out mass of the control volume here, so basically I can take the difference between this one here. So what is the difference between this one here for a constant mass? So for constant system mass, right? So which means that this part here and this part here is equal, right? So this side here and this side here will be equal, which means that the change with respect to the mass of the control volume will be equal to the delta mass in minus the delta mass out. Okay, this is a way that we're trying to do the analysis or find out the relation for the mass flow rate or the conservation of mass of a certain control volume. So now we can say that the change of the mass of the control volume is dependent on how much coming in minus how much going out. Okay, we can write the same equation here, but now we differentiate with respect to the time, or we can take, can say it is in the rate form. Rate form mean here is like differentiate with respect to the time. So you can see here this equation now. If I take the rate form, so dm of the control volume will be dm of the control volume with respect to dt. Same thing here for mn over t, it will be mn, and this will be m out. I can take the whole two term here, I can push them on one side just to make the equation equal to 0. So this will basically at the end it will be dm control volume with respect to the t. This minus here will be positive, so m out minus mn equal to 0. Okay, and this is what we call it the conservation. So basically here, blank, sorry. Oops, sorry, guys. So dm of the control volume with respect to the t plus m out minus m n equals 0. And this is my conservation of mass. Okay, so this is a conservation of mass equation. Okay, looking at the control volume, what happened to the control volume, what is going out, what is going in, right? This will give you the total will be equal 0 based on the control conservation of mass. Conservation of mass here mean the mass is of the system is equal 0, which mean is here, or the change of the mass with respect to the system is 0. That means a constant. Sorry, it's here. I can just constant here. Okay, the mass of the system is constant. So considering the mass is constant, because conservation of mass, whatever coming in, right? You can say that Mn in this side minus M out equal to the change within the control volume. Okay, so this is our conservation of mass. How about for a steady flow? What does steady mean? What is steady mean? Oh my God, guys, please try to be engineer when you speak and write. I know it's hard, but you know, we're kind of working on that. Okay, same. So what is same? What is same? Okay, no. What constant? No. Okay, all this is just like not engineering. Laminar. Oh no, this is not engineering. Nothing. This is engineering. Nothing. Not scientific. Steady mean what? Steady mean one thing. Hydrostatic. Nothing related to this. Hydrostatic mean constant, zero velocity, right? This is what hydrostatic means. There's no motion, no fluctuation. All this is, okay. All this is not the right answer. Velocity is constant. No, this is not. Velocity is constant mean no acceleration, right? Steady mean what? No acceleration. No acceleration actually, Diane, is like, you know, it's a byproduct of this. No change. No change what? No change of what? We are studying fluid mechanics, right? I agree. We're studying fluid mechanics. How about if we study solid mechanics? How we study, like, you know, biology system? We're talking about steady. What steady mean? Density change? No. You know, I'm gonna start getting disappointed. Okay, no. Steady. So far, you haven't taken any course talking about steady state situation. Steady what mean? Okay, all this is wrong. Don't get offended, okay? But this is all is wrong. Any steady means, yeah, you're getting closer. You know, equilibrium. System is equilibrium. Yeah. What means the system reach equilibrium? Yeah, not changing respect to what? Like, you know, okay, steady mean constant. You see, you got time, Zena, right? Time. It is respect to the time, right? Because you can have no change with distance. For example, here and here and here is the same, right? The only right answer to this is steady state mean no change with time. Some people trying to get into this, like by saying equilibrium. Equilibrium mean reaching a steady state, right? Steady state mean is basically with time. So every time that you see a term steady, every time you talk about steady here is with respect to time. D by dt is what? Anyone now after we know this? D by dt of what? Of what? Any say, anyone? Of what? D of dt of what? For a steady. Of anything, any variables, any quantity in the system, right? It is absolute, like, you know, anything that is with time is not changing with time. Okay, so which means that d by dt of any quantity that is 0, right? So if we are talking about steady flow here, that means this term here looks like it's gonna disappear, right? So in this case, if I have a steady flow, the inlet mass equal to the outlet mass, right? And this is what we call it the simple continuity equation. So continuity equation is simplified form of conservation of mass, right? So, and why it's simplified? Because it is a steady flow, right? So you can see here, imagine I have a simple pipe like this, flow coming in, flow going out, M1 flow rate, and this is M2, right? So this is basically equal. That means both of them are the same because it's steady flow, because no change with time. So there is no accumulation inside. There is no variation inside with time. That means M1 and M2 is okay. What is the mass flow rate? At 1, in general, it's rho, right? 1 A1 V1, right? And the mass flow rate at 2 is rho 2 A2 V2, right? And you can say this is the average velocity and this is the total cross-sectional area. This is we call it, this is a continuity equation, okay? Does density 1 and density 2 has to be equal? Do they have to be equal? Density 1 and density 2? No, it depends on the type of fluid. If the fluid is liquid, yes, density is the same. And this is what I'm talking about here. So this is just a more explanation of what I just explained to you now. So M is equal M, and we call this is the mass of the summation of mass, because not all the time it's only one in and one out. It could be multiple in and multiple out. So you can say summation of the control surface or the boundary. This is the control surface. Here is your boundary. So see how many coming in and how many going out. It just happened in this case, it's only one in and one out. But in general, it could be multiple in and multiple out, okay? So, and density, if the density for incompressible fluid is the same, so if density is constant, I can divide both sides of the equation by the density, and in this case will be A1 V1 is equal to A2 V2. Remember, this is an average area, average velocity, and this is the total area. Okay. Let's look at this example here. So I have a steady viscous flow through a circular tube. The axial velocity profile is given that much. Okay. M here is 0.5. So it's giving you the equation here. That is the velocity at any R. This UR is U naught. U naught here is your center velocity. 1 minus R over R times 0.5. Okay. He is asking to compute the average velocity if the density is constant. So density here is constant. Okay. How to find out average velocity? Remember, average velocity is, you need to find out the total flow rate, and you divide it by the total area, will give you the average velocity. It just happened to be like, you know, we have a circular duct here. Okay. So at any R, the velocity is like UR. Okay. So let's start this problem. So I have, so let me look from this side here. Okay. So now if I have an element like, you know, at any R here, at any R, do you agree with me that the velocity at every point here is the same? Yeah, okay, right. So now what is the Q in this area, because of course the Q is, the flow rate is going through an area. So not on a point, right? Not in a small, right? It has to have some thickness. So you can see there is an area coming in, right? So the flow that is going on here. So this dq here, if you take an element like this, I'm gonna call this is dr, right? And now the area I'm talking about here is a small little differential area. And I know for sure you have studied this in your maths when you took the math course, right? When you have a differential element here, this is the area. So dr here, right? And the velocity here is u of r, right? So if I need to find out dq here is, you agree with me that it is the area times the velocity, right? So the area here is, it's the velocity, which is u as a function of r, times the area, but the area here is dA, a small little differential area. What is dA here? What is the area here? Can you tell me? What is this dA here? What is the area here? All this area. Quickly, please, guys. I need to finish a certain amount of information today. Okay, what is the area of these elements? What do you call this element? It's a ring, right? By r square. Oh, this is the total area, Leanne. Right? What is the element in this area here? Guys, what happened to you today? So how can I get this 2 by r dr? Amazing, right? Right? Basically, what is that? It's, if you take this element and cut it, it will be a long strip like this. This is dr. And the distance here is a circumferential, which is 2 by r, right? So dA here is 2 by r dr, right? So dq will be basically 2 by r d u of r times 2 by r dr. If you need to find the total q, you just need to integrate from 0 to r capital, which is this r here, right? So you just need to go over the whole area, subtract them. I don't know what you're talking about. So 2 by r dr. So the total q will be this value here. Okay, now I just need to replace ur as a function of r, because basically I just need to integrate this in order to find q. So q here is, I'm gonna integrate with respect to the r. ur here is given as u naught 1 minus r over r to the power of 0.5. This is the equation that is given in this problem. And the area here is 2 by r dr. It looks like this 2 by is constant. U naught is a constant. This is just a constant, right? A constant value. I can just take it out of the integration. Okay, so q here will be an integration of r. Again, forgot to put u out, and this is 2 by out, and then 0 to r, and now I have 1 minus r over r 0.5, and this is dr. Now I can do the integration, because basically the integration is telling me that integrate this equation with respect to the r, and of course it's a function of r. What will be the integration for this? What is the integration before? Yes, r dr. Excellent. Thank you so much. What is the integration of this? How can I integrate this? Okay, let me remind you with some of the mass, right? Because we have a function here that is, it's not like r squared dr, so it's very simple integration. It is multiplied by 1 minus r over r. So in order to simplify this equation for integration, right? So what we can do is here, like we can do, like let's say, for example, here, let x is 1 minus r over r. Why I'm doing this? Because there is an exponent here that is 0.5. Okay, so if I have x that is equal 1 minus r, just any variable x, okay, just simplify it, 1 minus r over r. Dx mean, it looks like if I take the x here, I differentiate x, I will have to differentiate on the other side with respect to r. So it's going to be 1 is going to be 0, and then minus dr over r. So this is one of the things. So which means that dr here is, it's minus r dx. Okay, what else? When I am integrating with certain limitation, I have to consider the the limits of the integration. Okay, so r is, from the same equation, r is one minus x times r from this equation, right? So again, we can do this, right? The limits at r equals 0, x is, sorry, r equals 0, x is, you see here, r equals 0, x is equal 1, right? At r equal r capital, x is equal, see here, at r equal r capital, x is equal 1 minus 1 r over r, which is 0. So x is equal 0. Now I can change the integration now to q is equal to by u naught. And now I just change the integration here is with respect to the x, right? So it's going to be like x to the power 0.5. R is, you see here, R here is R times 1 minus x, right? And dx is, you see here, dr is equal to dx, right? dr is equal to minus r dx, right? There's minus here at the beginning of this, right? I can take the minus in this here. Now I convert the whole thing into minus 2 by u naught r square, right? This is constant. The limits here is when r is equal 0 is x is equal 1. When r is equal 1 or r capital, the x is equal 0. So now I have this integration is going to be x to the power 0.5, 1 minus x dx. It's a very simple integration here. Why? Because I can multiply this and then multiply that, right? So it's minus 2 by u naught r square. 1 to 0, x to the power 0.5 minus x to the power 1.5. All this dx. It's a very simple integration now. It's just x to the power value. When I integrate, I just add 1 to the exponent and then divide it by the new exponent, right? It's a very simple mass equation, right? So minus 2 by u naught r square. The integration now is x power 1.5 divided by 1.5, and then minus x to the power 3 2.5 2.5 divided by 2.5, and I put the limit between 1 and 0. Okay, Q here is very simple. You just do the limit here between 1 and 0, and you will find Q that is equal to minus 2 by U naught R square minus 1 over 1.5 minus 1 over 2.5. You can take this value here. It's going to be, this is going to be 0.26. So Q at the end is, I didn't calculate it. So you guys can sorry calculate it, right? This value here, right? What I'm interested in the velocity average, U average. What is U average mean? It is the total Q divided by the total area. So what is the total area in this case? Zero. No. Shouldn't be 0 instead of 1. No. You see the limit here? When R is equal 0, R is what here? When R is equal 0, you see here, R is equal 0, X is equal 1. When R is equal R capital, X is equal 0. So when R is equal R capital, X is equal 0. So the limit change when we change the equation. I can talk to you after this lecture, but this is just a simple little, mass thing, okay? So now average velocity is what? Average velocity is area total. What is the total area here? Oh yeah, you can use any simple, that's fine, yeah. Just use V average, V capital, but the most important thing, you know what I'm talking about, the average velocity. So the total area here is as if the whole flow is going over this area by an average velocity. The area total here is by which R? R capital, exactly, R square. So if you divide this by R square, it looks like, you see here, this is by R square. It looks like you will divide this by R square. U average here, or the average velocity here is, sometimes actually call it this way, sorry. Sometimes you call it like this, and then you put average here, right? Same thing. You do this, and you have this equation here, right? So it is minus. So you remember this minus here, there was a minus here, and there was a minus here. Multiplied together is going to be a positive value. And of course, the velocity will never be negative, okay? So this case is going to be like, a positive value. If you divided this by R squared, you will find that the average velocity here is 0.53 U naught, because what is left here is basically U naught, okay? So this is giving you an idea about, like, when you have a velocity profile, you need to find out total flow rates, you just integrate over the area, right? So just simple getting, like, the differential elements of area, and then integrate it over the whole. If you know the velocity profile, integrate over the whole area. If you need to find out the average velocity, you just divide this Q by the total area. Okay. So another problem. I think I will just finish this problem, though I needed more time to cover more other information, but that's fine. The pipe flow fills a cylindrical surge tank. So I have a tank like this, and the tank has a diameter of 75 centimeters. Surge tank here is like if the flow that's coming very fast here, or like, there is some disturbance of the flow suddenly, it's kind of absorbing the fluid here. So you might have a Q at 1, Q at 2 here, but there are some Q that is coming inside this tank. Let's say Q3, for example, here. Okay. Okay. So I have The biflow fills the cylindrical surge as shown. At a time t is equal 0, the water depth in the tank is 30 centimeters. So, imagine now in the beginning, this level of the water inside the tank is 0.3 meter. Estimate the time required to fill the remainder of the tank. So there is flow coming in, right? There's flow coming here, and this is okay. First of all, it looks like this tank is filling, right? Which means that, do you think Q2 is less than Q1 or equal Q1? Less, right? And it looks like very simple here because the velocity here is 2.5, the velocity here is 1.9. Let me assume that the diameter here, the diameter here is constant. So you see the diameter is in both sides here is the same. So the area is the same. So once you have the area is the same, but the velocity is less, that means the flow rate is less. So water, that means density is constant, right? That means basically, right, its density is constant. That means I have an incompressible fluid, of course, right? And also, right, one of the assumptions we have to make here, of course, this is incompressible for water. What else? What other assumption we can make here? Can I make a steady state assumption here? Anyone? Can I make a steady state? Why? Excellent, Desmond. Why? Okay, yeah, not velocity. There is no velocity change with time here. The velocity here is function, it's 1.9, the velocity here is 2.5. Why this kind of problem is not a constant time problem? Exactly, it takes the tank to the system, the velocity, the level of the tank changing. So the mass of the tank is changing. That means, we cannot really say a steady state assumption here because the tank is filling, right? Which means mass of the system is changing with time, right? Okay. So in order to solve this problem, it's very simple. We can say that our equation, M of the control volume with respect to the T, is equal to summation of mass N minus summation of mass out. Okay. And the control volume I'm talking about here is this control volume here. This is the control. Okay. What is the mass initially inside this control volume? Remember, this is your, this is your diameter, right? So the area here is pi over 4 d square, right? And it is filled with this 0.3 at any time. This is your H, the head of inside the tank. So at any time, what is the mass of the control volume inside this tank? The mass of the control volume at any time is pi over 4 d squared times H, right? So this is a volume, right? Times so rho, right? The mass of the control volume is the volume times the density, right? So D with respect to the time is equal. Mass coming in, mass going out. I know it's gonna be like, 1250 in 1 second. So I'm gonna stop here and then we'll come back on next time. Just, I know some people have to run for another class, so next time we'll start at these points. Okay, guys? Yeah, for any time, like for the people who want to ask those questions for anything that we discussed today or previous ones, if you want to stay around, we can go over this. Okay? You're welcome. Okay, so let me stop recording. And for people you have a good day, guys. No problem, Mohammed. So let me stop recording, and then if you guys have any questions, we can